So yeah, we're here live from the Crown Plaza Hotel in Albuquerque. I'm joined with some people from TeslaTech right now. Let me see if I can switch the camera. There we go. So we're here with Russell Anderson and also Lucian Ionescu, who presented at the conference. Did you guys present already, both of you? And so we're gonna have Lucian and Russell Anderson talk and give us a little bit of an overview of what they presented. So Russell, it's great to have you here with us. This is great.
You know, I should say hi to Russell. Russell, I haven't talked to you in years. It's good to see you again, sir.
Buddy, how the heck are you?
Well, doing well.
What you been up to?
Oh, well, for the last several months, I've been moderating the conference, although Jeremy and Mark they've been having most of the fun. So they get to actually build stuff. I just act as traffic cop.
Yeah. Oh, where's the serial device? We want a serial device.
So that's a plus.
Yeah. And so, yeah, what I've done is handed the feed over. I've got it spotlighted on, and I guess we can almost switch things up, but I've got it spotlighted on Jeremy.
Tim, you can actually spotlight, my cell phone has a second view of the room. So you can spotlight both cameras and we'll get two views of the room.
Let me see.
Mark Sokol, I just came in.
Add spotlight.
There we go. Now we can have both views back.
Is that you on your phone, right?
That's on my phone, yeah.
Okay.
We have to do a little improvising like that. Okay, perfect.
Yeah.
Oh, wonderful. Actually, that looks pretty darn good. Okay, I will mute myself out.
All right. And you can, all right, so why don't we start with, you want to start with Russell or Mark? Russell or Lucian?
Yes, so I'm here with some contributions to gravity theory and experiments. I must say from the beginning that there are many various methods to put a view of what gravity is. And definitely it's not the new one. That is not. And to be brief, what I add is some foundations based on the standard model. Using the quark model and the structure of the electric charge, which gives a slight correction to what electromagnetism would give. And that's not a surprise for many of us who know that electromagnetism and gravity are connected. And then looking around, I stumbled upon the theory which anticipated this, let's say 40, 50 years ago, the theory of Frederick Alzopon, which anticipated that if you orient the nuclei and the spins of the protons and neutrons, then you should be able to control gravity. So now this foundation based on quark structure shows clearly that indeed that's what has to happen. So in some sense, we expect the experiments did by Alzopon to really lead to a control of gravity. So to make things simpler, the main point is people should know that gravity is not a fundamental force. It's derived from what I can refer to electroweak theory, but to just put it simply, gravity is not a fundamental force. It can be controlled. So people should start contribute to this amazing research, both theoretical and experimental, if they want to see in the next 10 years, say, Star Trek News at 10 instead of just the show. So
That's very interesting. You mentioned quarks. How does that play into the? I was saying it's very interesting that you're mentioning quarks and really going down to the fundamentals of what's inside the atom, what's inside matter. How does that relate to the Alzaphan experiment and theory?
So that's the key of, let's say, my contribution to his theory. So let's take a neutron. A neutron is theoretically neutral from an electric point of view if you view it as a pointwise charge. But the moment you look at the structure of a neutron built out of 3 quarks, down, down, up, with a negative 1/3, negative 1/3, and plus 2/3, which give a total of 0 electric charge. But the moment you look at this structure and then you take 2 neutrons with some spin orientations, then there is a rather a tensorial force acting between the 2, which in first approximation is 0. So in first approximation, it looks like they are neutral, but the correction, which is a tiny, tiny contribution, depends on the orientation of the 2 neutrons. And naturally, they will orient towards minimizing the energy, and that gives a tiny attraction, which justifies and is the candidate for gravity. So I say candidate because at this stage, we don't have a mathematical proof of the fact that this attraction equals Newton's, let's say, attraction and gives Newton's constant. But for theoreticians, this is a challenge. Prove that this tensorial attraction yields, and one can compute the universal gravitational attraction of Newton, and that would be an amazing result. So just qualitatively, it justifies that orienting the constituents of the nuclei, now let's say the spin of the nucleus overall, would affect the weight. And that's the, let's say, essence of Alzaphan's theory, for which now we have a standard model justification. So we expect the experiments to give positive results.
Do you think there's any limit to what this experiment can do in terms of weight loss? Can it achieve 100%?
There is a statistic fluctuation involved. So temperature will definitely play a role. And if it's room temperature, there, right? So you can orient, let's say 2%, 10% of the spins, but they'll lose because of the temperature and the motion. They'll lose the orientation. So temperature will go against this coherent process of orienting the nuclei. But otherwise, if you could lower the temperature as much as you want, then theoretically you could shoot for 99% of weight loss.
I'm shooting for 100. To make it, if you make it weightless, then it becomes equivalent to nothing, and nothing can travel faster.
100 plus.
Can travel faster than
Right. So I mean, at lower temperatures, like superconductive temperatures, we know that there is a locking mechanism of the in magnetic field. So probably there will be like a possibility to lock to 100% loss of gravity. And amazingly, if we believe in Einstein's, and we all do, that mass, inertial mass equals gravitational mass as a charge, then it means we're nullifying the inertial mass. Then there is no obstacle towards zigzagging wherever you want with a spaceship based on this new technology, which we expect in the next, I would say, 10 years or so.
we would expect to go to Alpha Centauri with such technology, right?
Yes, but the solar system would be for me.
That's what. Yeah, you want to go on a day trip to Mars.
And then, yeah, here at New Zealand, some ambassador went to Jupiter to discuss some environmental laws.
That's a great place to go check out the environment there on Jupiter.
Satellites, maybe.
So we also have Russell Anderson over here. Russell's actually been working with us at TeslaTech. Oh, are we going to Jeremiah first?
Jeremiah's got to go and give a presentation, a live demonstration. So I wanted him to just talk real quick because he's got a live demonstration that's coming up. So I'm gonna have him go. He's got to go downstairs and run. So we're gonna have him go real quick. I'm sorry to cut you off, Russell. Man, it's not an issue of importance or he's just